I wanted to give you an example of how to use Kirchhoff's voltage law in order to solve a series circuit, which is a circuit we've seen many times before. So I have my table here, I have my circuit. I'm just going to go ahead and just label what I know. So I know the total voltage is 3.3 volts. I know the resistors are 100 ohms, 330 ohms, and 220 ohms in order going around the loop. The other thing I'm going to do is I'm just going to label my voltages. Since this is resistor 1, I'm going to call this V1, I'm going to call this V2, and I'm going to call this V3. That's important when we're looking at our voltage law. Now the other thing we have to do is when we're going to create our loop, and in this case we only have one single loop here, we just need to specify the direction of the loop. So I'm going to say that we are going in a clockwise motion around the loop. I'm going to start out here with the power supply. And starting out with the power supply, from the bottom of the power supply to the top of the power supply, I know it's going from negative to positive, so it's going to gain potential. So because of that, if I just call this VT, I have a positive VT. And it's important to keep the sign straight when you're dealing with this. Now, if I add up the next element is V sub 1. V sub 1, I know it's going to have a certain amount of potential. It's going to lose some of its potential. So because of that, I'm going to put a negative V sub 1. Same thing with V sub 2. V sub 2 is the next element. It's going to lose some of its potential there. And then negative V sub 3. And then that's going to equal 0. This is how we create the equation. So it's really important to get the negatives in there correctly. Now, the next thing I can do is if I add V1, V2, and V3 to both sides, you notice what I end up with is that VT equals V1 plus V2 plus V3. That's our series circuit rule for this circuit. And so that's actually where it comes from. This series circuit rule is derived from Kirchhoff's voltage law. So I found that very important to show you. The next thing that I know is that for each element, Ohm's law applies. So if I look at V1, I know that V1 is equal to I1 times R1, which means that V1 is equal to I1 times 100 ohms. Same thing with the second voltage and the third voltage. So I can say that V2 is equal to I2 times 330 ohms, and I can say that V3 equals I3 times 220 ohms. Now it's important to understand that the currents are the same. And the reason why the currents are the same, if you really wanted to look at the nitty-gritty, it's because of KCL. If I have I1 coming into this node here, and if I have I2 coming out of this node here, there's only one current going in, there's one current coming out, so they must be equal to each other. So the currents must be the same. So I1 equals I2, I2 equals I3, I3 equals IT. That's why it actually ends up being the current around a series circuit is the same, and that's because of KCL as well as KVL. So because of that, the currents here are all the same as the total current. So if I just replace all three of these I1, I2, I3s with the total, that means this is just the total current times 100 ohms. This is just the total current times 330 ohms. And then V3 is just the total current times 220 ohms. Now I'm just going to substitute these back into our equation. So I know that V1 is the total current times 100 ohms. I know that V2 is the total current times 330 ohms. Didn't need to put the parentheses around IT. And then V3 is IT times 220 ohms. And that equals the total voltage. I know the total voltage is 3.3 volts. So what I can do now is I can solve this. I can just combine these three together. You'll notice that the resistors add up. That's going to be our total resistance. That's where that comes from. And then I can find our total current. So if I just add up 100 plus 330 plus 220, that's my total resistance, which is 650 ohms. Now if I take 3.3 volts divided by that, that's going to be my total current. So I get a total current of 0.0051 amps. I'm just going to round to 4 decimal places here. Again, it's important to keep in mind that you don't want to round too much here, so it's probably best to use the same value from the calculator when you're figuring these things out. But in this case, since I'm not going to write out 8 decimal places, I'm just going to round to 4. That's my total current, 0.0051 amps. Now I know that's the same, so I can fill in the table with my currents. And then all I have to do is just use Ohm's law again to find out my individual voltages. So if I go back to this, and if I just multiply 100 times the current, I'm just going to use the value from the calculator. I get 0.5077 volts, rounded to 4 decimal places. For the next one, I get 300, oops, no, that's wrong. 330 times the current is 1.6754 volts. And then the last one, 220 times that current, is going to give me 1.1169 volts. And these should add up to be about 3.3 because a rounding is going to be off just a little bit. But in a perfect situation, it should add up to exactly 3.3 volts. But it's the same type of analysis, and it's the same type of result that you would get if you just use your series circuit rules. The series circuit rules come from KVL and KCL, and that was the whole point that I wanted to show you with this problem.